So what I'm going to walk you through here is the force diagram and the analysis for what's called a semi-Atwoods machine. It's very similar to what you did in your lab, where you have the air cart and it's attached to a string. It's sitting on an air track, and that string goes over a pulley, and there's some weights hanging on the other end of that string. So for our force diagram, we're going to start here with the force diagram for the glider or the cart. I have my surface, I have my dot. It's going to have the force of gravity on the cart by the earth, and then the normal force on the cart by the track. Those are going to be equal forces because the cart is not accelerated in the vertical direction, so the forces are going to be balanced. The next force we're going to have is a force of tension on the cart. We're going to say it's by the hanging mass. We're not going to say on the cart by the string. That's a little bit of a change from earlier, but because the hanging mass is sort of what's causing that force, we'll say on cart by the hanging mass. And we'll assume for now that there is no friction, and later we'll do a problem where we address what to do if there is friction. So the next object is the hanging mass. There's a force of gravity on the hanging mass by the earth, and then there's a tension force on the hanging mass by the cart. Again, we're not going to say it's the string, we're going to say it's the cart because that's what the string is attached to. So this is by the cart here. You'll notice when we look at these forces that the force of gravity is larger than the tension force. That's because this hanging mass is going to be accelerating downwards, so it needs a net force in the down direction, and therefore the force of gravity is going to be bigger than the tension force. And then over here on the force diagram for the cart, you'll notice that in the x and y, or the x direction, the force of tension is the only force, and so it will also be accelerating because those forces are unbalanced. We know from Newton's third law that if object A, like if the cart exerts a force on the hanging mass is going to exert a force on the cart in equal and opposite directions. So these are third law pairs, so we're going to mark them as being equal forces and a third law pair. You notice that the directions aren't exactly opposite. That's because of this pulley up here. And remember, what a pulley does is it changes the direction of force, and that's important in this problem because things are going to get a little bit weird with directions because the objects are actually moving in two different directions, and because of this change in direction of force. So don't forget about that pulley. Next thing we want to do is we want to draw a force diagram for the entire system. And when I say the entire system, I mean the air cart and the hanging mass here. So my next force diagram for this dot here is going to represent both the cart and the hanging mass together. And this is kind of weird. It's a little bit of a different way of looking at it, but it'll help us with our analysis. So we're going to look at it in a non-intuitive way that'll make our problems easier. So this dot is the cart and the hanging mass. Nope, this is pass, it should be mass. So what force is acting on this entire system? The tension force is not on the system at all, because the tension force is between the cart and the hanging mass. But the cart and the hanging mass are both represented by this dot here. And an object cannot exert a force on itself. So we can't put the tension force in our force diagram that represents both the cart and the hanging mass together. So the only force that is not within the system is we have a force of gravity pulling down on the hanging mass. So we have a force of gravity, and I noted it's the force of gravity on the hanging mass, on the system by the earth. We're going to do a simplification here. We know we're going to have a normal force on the glider and a force of gravity on the glider, and we know those are going to add to zero, so I'm going to leave it off this force diagram. Again, we're kind of breaking some rules here, but this is a little bit different problem because we have two objects that we're treating as one. So this is one way to do it, or we could look at the force of gravity on this weight here as pulling down. So same Fg hanging on the hanging mass on system by the earth. And the reason we can do it either way, so the down comes from the fact that over here on the hanging mass, the force of gravity is pulling down on it. The to the right comes from the fact that on the glider essentially is getting pulled to the right. This force of gravity force is kind of getting, the direction is getting changed by this pulley. So I know it's really weird to have force of gravity going to the right, but since the glider is moving to the right, it's acceptable to do that on here. Or since the hanging mass is moving down, its net force is going to be down, we could draw it going down. Either one of these works. I think this one on the right hand side is going to make more sense to some people because the force of gravity is going down. But on the other hand, I think this one makes more sense to people because the glider is moving to the right. Whichever way makes more sense to you, you can use it. Either one. So what if there is friction? So if there's friction, this friction is going to be on the glider part of the system, and it's going to be going to the left up here. So on our first force diagram, we can add the friction to the left. It's the force of friction on the cart, or the glider, on the system by the track. Or if we go over here, there isn't really a force of friction on the weight, but remember our system is this entire weight and glider together. And if we say the force of gravity is going down, the friction force is going to be opposing that. So we can actually draw the friction forces going up. Again, that seems kind of strange, but you need to understand that there's a force that's pulling down here, and it's translated, going to the right here, and then there's a force that's acting to the left over here, which is the friction force. So this is kind of like the FG. So we're getting pulled to the right and we're getting pulled down at the same time because I told you this was going to be important. That pulley is changing the direction. So you could do either one of these force diagrams. Either one is okay, whichever one makes more sense to you. On one hand, it's weird to have force of gravity going to the right. On the other hand, it's weird to have force of friction going up. So let's do a practice problem. Mass of the glider is going to be 0.3 kilograms. Hanging mass will be 0.05 kilograms. The friction will be 0.1 newtons. And I want you to find the acceleration of the cart mass system and the tension in the string. So go ahead and pause the video now and see if you can find those things. All right, let's check your work, or maybe you need some help. So I'm going to start off with the force diagram that has things going horizontally. Again, you can do either one. I'll do both. And I'm going to calculate Fg. Remember, this is Fg on the hanging mass, so that's just 9.8 newtons per kilogram times the mass of the hanging mass, which was 0.05 kilograms, which I said on the last slide. So we get a force of gravity of 0.49 newtons. So this is 0.49 newtons here. And it's going to the right, so we'll say it's positive. Next, I want to get the friction force. Oh, that was already given to me. It's a negative 0.01 newtons because it's going to the left. So this is negative 0.1 newtons, my force of friction. So I can apply my equation here. I'll do these up all at once, walk through them. My Newton's second law tells me that acceleration is equal to the net force divided by the mass. My net force is just going to be the force of gravity, which in this case is going to the right, minus the force of friction, which is going to the left. Again, we're ignoring the normal force and the force of gravity on the cart, just to make things simpler. And then divided by the mass of the entire system. And this is the most, I don't say it's the most important, but this is the thing that students forget the most easily. This whole system is accelerating, both the cart and the hanging mass. So we need to do the mass of the cart here by the 0.3 kilograms plus the hanging mass, which is 0.05 kilograms. I compute this and 1.1. I'm going to round it to 1.1 meters per second squared just so it fits here. We're going to have a rounding issue later, but so if you want to keep a few more decimals here, your numbers will come out a little bit better later on. So 1.1 meters per second squared is the acceleration of this system. Positive 1.1 makes sense because our net force is going to the right here because that force of gravity is larger than the friction force. So positive F net, positive acceleration. Now let's do the same thing over again, but with this other view of the system, this vertical view of the system. Same thing as before. Fg, but it's going to be negative 0.49 newtons. I only want the Fg on the hanging mass, and it's negative because it's going down. Fk is 0.1 newtons. In my force diagram, it is going up, so it's positive. It's opposing the FG, so it has to have the opposite sign. And then I'm going to do the exact same thing I did before. I'm going to plug in my two forces, add them together. Force of gravity is negative in this case because it's going down. Force of friction is positive because it's 0.1 newtons. And then we have the mass of the system added together. Force of friction is positive because it's going up. It's opposite force of gravity in terms of the direction of motion here. And I get negative 1.1. Well, hey, that's a negative sign. That's different from before. Well, it's different from before because from this viewpoint, we have an F net that's going down. Our system is moving in two different directions at once because it's going to the right and it's going down, so that's why I have a negative F net. All right, so how do we calculate the tension in the string? Why can't we just use the force diagrams we used? Because there is no tension in this force diagram. Tension force isn't here, so none of these equations will have tension in them. So we're going to have to go for our original force diagrams from this slide here. So this is the original force diagrams. Notice there's a tension here, and there's a tension here. Again, we're going to do it twice. First, we're going to do the force of tension on the hanging mass. So this dot here represents just the hanging mass. This is only the hanging mass here. So the force of gravity on the hanging mass only, and the force of tension on the hanging mass. Use the net force divided by the mass. So net force is force of gravity plus tension. I can calculate my force of gravity is negative 0.49 newtons. Force of tension, this is what I'm solving for. This is the hanging mass. It's the mass of the hanging mass only. And this is the acceleration I found in the other problem earlier. So remember, my acceleration with this force diagram was negative, so I'm going to do negative here. Just solve for the force of tension, multiply both sides by 0.05, then I'm going to add 0.49 to both sides here, solve for Ft, remember this is the variable I'm going after, and I get 0.435 newtons. So this is the tension. Newton's third law says that this tension here on the hanging mass by the cart is going to be equal and opposite to the tension on the cart by the hanging mass. So let's go see if that's the same. And this is where we're going to get the rounding error, just a heads up. So this is my other force diagram from earlier. This dot represents just the cart. And what we're going to do is we're going to have the forces in the x direction. So force of friction, force of tension. Because this is the force of tension on the cart by the hanging mass. Because we're just looking at the cart here. So friction is negative 0.1 newtons, going to the left. 0.1 newtons was what I was given earlier. This is the mass of the cart, and here's my acceleration that I calculated earlier. Going to do the exact same algebra as before, solve for Ft, and I get an Ft of 0.43. And this is the rounding error because if we kept all the decimals on the acceleration, we'd get a closer answer to the other one, but it's close enough. We get the same tension in both of those, because on the last slide, go back here, we had 0.435, and now we have 0.43. So the tensions are the same. So that's how you find the acceleration of the system, how you find the tension in the cable, and the acceleration for the cart and for the hanging mass are going to be the same because they're connected. They're all moving together. So there you go. That's how you do it.